Greetings to all. I am Dr.G.Sindhu, Assistant Professor and Head of the Department of Mathematics Self-Financing, Nirmala College for Women, Coimbatore. I welcome you all to this module. In this module, we'll discuss about an important property of complex functions, namely singularities. As the function behaves in an anomalous manner at singular points, this property must be treated separately when analyzing the function or the mathematical model in which they appear. In this module, we'll define singularities and study its classification with examples. A singular point of a function is a point at which the function ceases to be analytic. In other words, the point z equal to a is a singular point of f of z if any of the three properties are satisfied. Number 1, f of z equal to infinity, or if f of z is not defined at z equal to a, or if f of z is not differentiable at z equal to a. There are two types of singularities, namely isolated singularities and non-isolated singularities. What are isolated singularities? If z equal to a is a singular point of a function f of z, and if there exists a neighborhood of z equal to a containing no other singular point of f of z, then z equal to a is said to be an isolated singular point of the function f of z. As an example, consider the function 1 by z into z minus 1. Here, 0 and 1 are the isolated singularities. If f of z has infinite number of singular points in every neighborhood of z equal to a, and it forms the limit point of this set of singularities, then it is called a non-isolated singularity. Example, consider the function f of z equal to 1 by sine of 1 by z. This function vanishes at the points z equal to plus or minus 1 by n pi, where n varies from 0 to infinity, and z equal to 0 forms the limit point of set of other singularities. Hence, 0 is a non-isolated singularity, whereas infinity is an isolated singularity. Isolated singularities are classified into three different groups. They are removable singularity, pole, and an essential singularity. This classification is done with reference to the negative powers of the Lorentz expansion of the function about the singular point. Removable singularity. If the Lorentz series about z equal to a of the function valid in a deleted neighborhood of z equal to a has no negative powers, then we call it a removable singularity. Alternately, the condition limit z tends to a f of z exists and is finite, then z equal to a is a removable singularity. In the given example, at z equal to 0, the limit of the function is 1. Hence, 0 is a removable singularity. Pole. The Lorentz series about z equal to a of the function valid in the deleted neighborhood of z equal to a has a finite number of negative powers, then we call it a pole. Alternately, if limit z tends to a f of z tends to infinity, then z equal to a is a pole. For the function e power z by z equal to 0 is a simple pole because its expansion about z equal to 0 has only one negative power in z. Essential singularity. If the same Lorentz series expansion about z equal to a has infinite number of negative powers, then it is an essential singularity. Alternately, if the same limit does not exist at this point, then we call it as an essential singularity. In the given example, z equal to 0 is an essential singularity as the expansion contains infinite number of negative powers. Thus, we have seen the behavior of the functions at their singularities. Thank you for watching this module.